Namaskar and welcome back again to our series of lectures on development and applications of special concretes. We'll continue the discussion today with proportioning of concrete mixes, and what we'll do is the analysis and adjustments. Sometimes the proportions that we determine need to be adjusted. Also, the analysis that we do today, I hope, will give you an insight into what concrete as a material is and what is the role of cement, paste, mortar, and finally the coarse aggregates in the whole system. And before we get started, this slide and the next two are the customary slides that I'm showing you all the time, basically to orient you in the direction or in a thought process that I have towards concrete. It tells you what I think. Some of it is fact, some of it is a model that I have in my mind. The fact is only water, cement, sand and gravel are constituents of normal concrete, which ranges from several microns to several centimeters. They're all heavier than water. Water is the only liquid constituent. And as far as our desire is concerned, we want concrete to behave like a liquid when fresh and like a rock when it's hard. This tells you another fundamental model that I use. Paste being a suspension of cement in water, mortar being a suspension of sand in paste, and concrete at the end of it being a suspension of coarse aggregate in mortar. I hope that the analysis that we'll do today will help you understand this model which I have been trying to talk to you all the time. Cement and water are the only reactive components, and fine aggregate and coarse aggregate are inert and used as fillers. And the issue of constituents, proportioning, properties, and the method and environment of construction are all intertwined. So what we are trying to do as far as this particular module is concerned, we are trying to review the properties of fundamental concrete, that is normal concrete, and we will move on to special concretes, possibly in the next lecture or maybe the lectures after next. This is another picture which just shows you a real graphic picture or an image of aggregates being suspended in mortar, the coarse aggregates being suspended in mortar. Now, as far as proportioning is concerned, we've seen this slide before. The objective of this exercise is to find a suitable combination of the relative amounts of sand, water, coarse aggregate, and cement so that the concrete has the required properties in the fresh and hardened state and meets any other requirements that the client or the codes or a particular structure might have. What we've done so far is that based on a simple algorithm and the principles that we've discussed, some experiments, properties of constant materials, and the desired properties of concrete, we have tried to do the determination of the proportions of a concrete mix. And the exercise was largely volumetric. We went to the extent of saying that, okay, we will have 1,000 liters pitcher or 1,000 liters of fixed volume, and we will have cement, water, sand, and coarse aggregate, the absolute volumes of all these filling up this 1,000 liters. Of course, there was the air content that we have always taken to be a given as a granted or an input to the exercise. Having said that, what we'll do today is we'll do an analysis of the proportions of ingredients we obtained in the last class, a small bit of that. Then we'll go to adjust or revise a predetermined proportion, such as the one that we got last time, such that we'll go to adjust or revise a predetermined proportion based on the principles, should there be a need, and we'll try to do the proportioning of a concrete mix with chemical and mineral admixtures. So this is the 3-point agenda that we have as far as the discussion today is concerned. So coming to the first bit, which is the analysis of the proportions of ingredients we obtained in the last class, we had set out to proportion an air-entrained concrete with the parameters 5% air, 160 kgs of unit water content, a water cement ratio of 50%, and an S by A of 36%. And with that, we had determined these to be the proportions. This is by volume and this is by weight or mass. Now, If we look at it closely, we see that the cement is 103.2 liters, water is 160 liters, fine aggregate is 247, coarse aggregate is 439.6, and these are the values in kgs per cubic meter. So if we look at the relative volumes and the relative masses of these different constituents by way of percentage or in terms of percentages, we see that cement constitutes about 10% by volume and 14% by weight. As far as paste is concerned, that is cement plus water, that constitutes about 26.3. Maybe in some cases it may be a little more. 25 to 30% is what is paste. By mass it's about 21. Mortar is about 56%. It ranges in different concretes from about 50 to 60% by volume and about 50% by weight. Coarse aggregates in this case turned out to be 44% by volume and about 50% by mass. Please notice that the inert material is more or less 2/3 the total volume and accounts for about 80% of the weight of concrete. Also, cement is the most expensive material in the whole mix. So as far as the expense is concerned, cement is the most expensive of the materials and coarse aggregate possibly is the cheapest. So the basic thought process that traditionally we have is that we should try to maximize the amount of coarse aggregate in the system and try to minimize the amount of cement from a strictly economic point of view. But the economic point of view is something which will come later. First of all, we'll stick to the technical aspects, and that's what we are doing right now. Let's move on to the second objective for the discussion today. How do we adjust or revise a predetermined concrete proportion should there be a need? When does such a need arise? The first case where the need can arise is if the concrete does not have the properties we assumed or targeted. Also, it can happen that the material properties which we are using at a construction site change. For example, the fineness modulus of the sand may change. There may be a change in the properties of cement or the chemical admixture and so on. So there are so many reasons because of which an adjustment in the mixed proportions can be required. How do we go about doing that? Now in the present case, we started with the idea that the slump of the concrete should be 8 centimeters and the air should be 5% by volume. That was the basis for carrying on our proportioning exercise. Now suppose it turns out that in actual case or in reality we get 7 centimeters of slump and 4% of air, which is different from the slump that we targeted and the air that we targeted. It could be that one of them matches, the other doesn't match. So it could be any combination. So just for the sake of argument, we are taking this situation where the actual slump is lower by 1 centimeter and so is the actual air content, which is lower by 1%. Now, in order to adjust the air content, what we really need to do is to use an air entraining admixture. In fact, for all AE concretes, an air entraining admixture for all AE concretes, an air entraining admixture is an integral part of the mix. Now, we've discussed this before, that the admixture manufacturer would give you certain specifications and say that if you use a certain dosage of this admixture, you will get a certain amount of air entrained in the system. That may or may not be necessarily true, and perhaps that could have happened in this case as well. We fixed a dosage, thought that it will be 5%, but it turns out to be only 4%. So for this adjustment, what we'll need to do is to adjust the dosage of the air entraining admixture that we use. Apart from this, what else do we need to do? Now here is a reference table for minor adjustments in the mix. This has been taken from the JSC specifications for concrete structures, and it says that if the fineness modulus of sand changes by 0.1, you need to correct the S by A that you have by plus 0.5. So an increase here is a plus here. You don't need to adjust for water content. For each centimeter increase in slump, you don't need to correct for S by A, but you need to add water to the extent of 1.2%. So increase slump, increase the water. In order to increase the air content, or if you want to increase the air content for each percentage increase in the air content in the concrete mix, you need to reduce the S by A by 0.5 to 1%, and you need to reduce your water content by 3%. Recall that I had already discussed that if you increase your air content, your workability increases. And in order to compensate for that increased workability on account of increased air content, you really need to reduce your water content. And that is what is suggested here in terms of minus 3%, and so on. So once you have this kind of a guideline or guidance available to you, we are ready to modify our mix. So as far as we are concerned, in our particular case, we want a change in the slump value and we want a change in the air content. So how do we go about doing it? We need to do the S by A corrections here, and we need to do the unit water content corrections here. So that's again a reiteration of what we wanted, 8 and 5, and what we got, 7 and 4. So the slump here is in centimeters and air is in percentage by volume. Now if that happens, from the previous table we know that there is no adjustment here, minus 0.5 to 1 here. We need to go to plus 1.2 here, minus 3 here. So as a result, if we take this information here, none, minus 1, plus 1.2, minus 3, we do an algebraic operation and say that, okay, the net result is that we'll reduce the S by A by 1% and we will reduce the water content by 1.8%. So if we want to do that, the water content becomes 160 is what we had, 2.9, which is 1.8% of that. We get 157.1, let's say 157. Similarly for S by A, we have 36 minus 1, which is 35. So we don't want to change the water cement ratio because that is something which will be governed by the strength considerations, and that's not on the table right now. So with these modified parameters, we are ready to go. The original mix was proportioned as an air-entrained concrete with these numbers, and the mix has to be redesigned using, this doesn't change because that's a given. The water content has been changed from 160 to 157 like I showed you before. We are not changing this. The S by A is becoming 35 instead of 36. Of course, there will have to be an adjustment in the dosage of the air entraining admixture to increase the air content because we got 4% whereas we want actually 5%. So having said that, if we do this exercise, and I'm not going through the details of the algebra, this is what the modified mix would look like. 157 kgs of water, 314 kgs of cement, water cement ratio being 50%, translating to 101.3 liters of cement. With this volume, the inert material here, that being proportioned using 0.35 instead of 0.36, you get 242 and 449.6 here. Use the specific gravity values to get the fine aggregate and coarse aggregate content in terms of kgs per cubic meter. So that is your modified mix. If you want to summarize it, this is what it looks like. 160, 320, 645 and 1156 becomes 157, 314, 631 and 1182. So as the water has gone down a little bit, cement has gone down a little bit, you reduce the S by A, that has had its effect, and as a result of that, all this volume reduction has been consumed by the increase in the coarse aggregate. Of course, I'm leaving it to you to construct a similar table by volume and then study how the things have changed. There would be, of course, marginal changes, and that's something which I'm leaving to you as a small assignment. Now, With the revised mix, we can only hope that the desired slump and air content, which is 8 centimeters and 5%, is met. It may not happen and we may have to go back to the drawing board and carry out another iteration. Then there is uncertainty about the properties obtained in trial runs to be replicated in the field. Oftentimes, as far as mix design is concerned, or proportioning of concrete mixes is concerned, this exercise is carried out in the lab to get a mixed proportion, and then that mixed proportion is taken to the field. Now, the field conditions are quite different from that in the lab. For example, the mixers could be different, the power of the mixer could be different, the temperatures could be different, and so on. Therefore, how do we ensure that what we have determined in the lab, whether it is 8 centimeter slump or 5% air or whatever it is, that is what we will get in the field also? Very difficult question to answer. Concrete proportioning or proportioning of concrete mixes is not a very well developed science in that sense that, okay, if I use 160 kgs of water and 320 kgs of cement, we'll always get a certain strength. We use a certain amount of S/A, we'll always get the slump. No. The properties of the material affect these properties like slump and air content or bleeding, setting time, and so on. And therefore, at the end of it, this exercise has to be repeated, and it is only a trial and error procedure. So now, in that kind of an environment, how do we make sure that what we get in the lab is what we will get in the field? So what we try to do in that case, or for that contingency, is that if the final requirement in terms of slump, let's say, is 8 plus minus 2 centimeters, or for air, it is 5 plus minus 1%, because at the end of it, people who write specifications also understand that there will be a certain amount of variation, whether it is in slump or its air content or any such number, and a certain tolerance is given. Now, we do not want to use all that tolerance when we do the trial in the lab. So what we try to ensure that as far as the recommendation of proportions from the laboratory trials is concerned, that matches or that meets a more stringent requirement. For example, we may insist that as far as the lab is concerned, we should be sure that the slump, even though 6 to 10 centimeter kind of slump is acceptable to the client or acceptable at site, as far as the lab is concerned, the number should be between 7 and 9. Similarly, for air content, we don't use the 1% here, we use, let's say, something like 0.5%. Hoping that with this more stringent criteria being followed in the laboratory, the situation can be taken care of a little bit more robustly when it comes to the actual concrete being used at sites or in the field. Now, having said all this, now let's move on and try to understand yet another way of specifying a concrete mix. This method basically says that we will fix the coarse aggregate content. We want the coarse aggregate content to be some number. Of course, for this example, I've taken it to be 48%. What this does is that it does away with our requirement for determining or working within S/A. We'll see how. So coarse aggregate is fixed, meaning thereby that we are really talking of proportioning now only the mortar content, which of course will include the air content. And if this number was 48, this number will be 52. So if it is given that we want a concrete which has 5% air, unit water content of 175, a water cement ratio of 50%, and we fix this coarse aggregate content to be 48%, then the proportioning is a 1-minute exercise. All that we need to do is, we know the air content to be 50, we know the water content to be 175, the water cement ratio being 50%, which is given here, gives me the cement content of 350, which translates to 112.9. We already have fixed the coarse aggregate content to be 48% by volume, and that is 480 liters, and that translates to 1262.4, and therefore this volume of sand is automatically determined to be 182.1, which translates to 475.3 kgs per cubic meter. So this is a different approach where we try to fix the coarse aggregate volume and try to just play around with the volume of mortar. As you can see here, when I say 48% of coarse aggregate, I am trying to say 48% by volume. So therefore, this specification or this method of specifying the mix does not require any S by A, because S by A was at the end of it only a parameter to tell you how much of sand is there in the entire inert volume. In this case, the coarse aggregate is directly specified and we can work out the fine aggregate from here. So with this, we move to the third part of the discussion, that is proportioning of concrete with chemical and mineral admixtures. Now this is something which is very interesting, gives you a lot of options and tests your mettle as a concrete engineer, and we'll see how. Let's say for an example, a normal concrete is proportioned with the following conditions: 5% air, 180 kgs of water, 45% water cement ratio, and the coarse aggregate content to be 40%. So I'm not using the S by A route, I'm using the coarse aggregate content route, and I'm specifying that to be 40%. We could very well go ahead and do the exercise of proportioning the mix, but the twist is other conditions dictate that the cement content cannot exceed 320 kgs. Assume that the following admixtures are available to you: a water reducer that can be used to reduce the water demand by 20%, and a mineral admixture with an efficiency of 75%. We'll talk a little bit more about these admixtures in a subsequent discussion, but I'm sure you'll be able to follow the discussion as we go in this class, because it's basically just a numerical example and it's going to be simple arithmetic that we will do. Now we need to carry out the exercise of proportioning the concrete with these conditions. This is the base and these are additional constraints. Now obviously we start with carrying out the proportioning in a normal sense, and if we do that, 5% air, 180 kgs of water, 45% water cement ratio, 40% coarse aggregate content, we get figures like this. This is by volume, this is by weight. Air we know 50 liters, 180 kgs, 180 liters of water, 400 kgs of cement translating to 129 liters of cement, and 40% here means 400 liters, 1052 kgs, and we have the fine aggregate to be 241 liters and 629 kgs. The problem is that this cement content is greater than the 320 which is allowed. So what do we do? This mix does not meet the other criteria of cement content, which exceeds the maximum permissible value. And this cement content can now be brought down using two options. One is to use a chemical admixture such that the water content for the same slump can be reduced and the cement content will automatically come down, because we are working with the water cement ratio there, and that has to be maintained at the old level because we are not trying to change the strength requirement. Or we could use a mineral admixture to directly replace cement. That is a partial replacement of cement using some kind of a mineral admixture, and the amount of this admixture would depend on its efficiency. So this is something which we need to explore and understand a little bit, and these are the two routes that are available to us. Let's examine the first route, that is the chemical admixture route. What does it say? if the maximum cement content is 320 kgs and the water cement ratio has to be kept at 45%, then the maximum water content that you can have is only 144 kgs. Because water cement ratio, if it is determined at 144, that will give you a cement which is 320. And that is the maximum that you can have. So you cannot have water more than 144. The problem in the previous discussion, or the basic discussion, was that the water content was much more than this 144, and therefore the cement content became much higher. Now how do we go about doing it? Use the chemical admixture. The chemical admixture that will reduce the unit water content from 180 kgs to 144 kgs, and this reduction of 36 kgs is about 20%. And the problem is reduced to identifying an admixture and its dosage, and that can be done through trial mixes. So here again, once we have a high range water reducer or a super plasticizer or whatever it is, that will also be prescribed as a dosage in terms of 1% or 0.5% or 0.75% by weight of cement. And depending on this dosage, we will get the extent of reduction in water content. So we'll need to do a little bit of search, talk to some manufacturers, read up their literature, find out what kind of admixtures are available, what is their power in terms of reducing the water demand for the same slump, and come up with an admixture and a dosage which will give us a 20% reduction. And as far as the given information is concerned, it did say that yes, some kind of an admixture which will be helpful in achieving this is available. So we more or less have the solution. We'll have to do some trial mixes and we are in business. So if we do that, what we have is air is 50 liters, 144 kgs of water brings my cement content to 320, which now becomes 103.2 liters. We have this volume now to be adjusted. Now this volume has to be adjusted, but the fact is that we are still keeping coarse aggregate to be 40%. This doesn't change, which means that only the remaining volume will be absorbed all by the fine aggregate. And this will translate to 790. So if you look at it from the previous discussion, that is the basic mix, we'll do a comparison shortly and you'll know what has happened as far as the previous mix versus a mix which has a certain amount of chemical admixture dosed into it to reduce the water demand from 180 kgs to 144 kgs. That is part of this mix. Now if we look at it from the previous comparison, this is what we had, 180 kgs. This is all by kgs per cubic meter. This is the cement, 400 kgs, which has been brought down to 320. The 129 liters has brought down to, or has come down to 103. 629 kgs of fine aggregate has increased to 790 kgs. So you can see that the total increase, there is substantial increase in the fine aggregate content, and that can be expected because what is happening really is that all the reduction that is happening in the water volume, all the volume that is being reduced from the cement is being absorbed by the fine aggregate, because the coarse aggregate volume is not being changed, and therefore there is a substantial increase in the amount of fine aggregate. But it also shows that the mortar content here is still 60% of the total volume. Of course, this is by mass, so I cannot really be plotting it here, be careful about that. But the mortar content in both cases is 60%. So effectively, the reduction in the paste content has all been replaced by sand in order to preserve the amount of mortar in the concrete mix. So this is the kind of thought process that you should have, or you can have, when we are trying to understand concrete in terms of that material, that is concrete, being a suspension of coarse aggregates in mortar. So there is a certain amount of mortar. What we are talking here, or what we have discussed here, is the amount of mortar. What we have not discussed here is the quality of mortar, the properties of mortar. And that is something which will take us into very specialized kind of discussions, which we'll possibly do at a much later point in time in this course. Now let's move to the other option that we have, and that is to use only the mineral admixture. We are not going to use the chemical admixture route, we are going to use the mineral admixture route and directly replace the cement partially. Of course, we only need to do it partially because 320 kgs is the cement which is still allowed, and we are going to use that. So basically what we need to do is to replace 80 kgs of cement. Now, given the fact that the efficiency of the mineral admixture that we have is only 75%, so we cannot replace it 1-to-1, we will need to replace this 80 kgs by 106.7 kgs of the mineral admixture on a per cubic meter basis. So once we understand this part, that instead of 400 kgs of cement, we will use 320 kgs of cement plus 106.7 kgs of mineral admixture. This will now meet our requirement that the cement content not exceed 320. So this is the other route that we are taking, and let's move and see what happens to the proportioning. So what we are doing here is we are keeping the water content same. Air is of course 5%, so water content is 180. Cement we've taken to be 320 kgs, brings it to about 103.2 liters. Replacing this 80 kgs is 106.7 kgs, and given the specific gravity of the mineral admixture to be 2.2, gives me a volume of 48.5 liters. This 400 liters doesn't change, so the fine aggregate becomes 218.3 liters, which translates to 569.8 kgs. So this is the trick that we have done in proportioning this concrete mix with only the mineral admixture. Of course, there's another option that instead of going whole hog with the chemical admixture route or the mineral admixture route, we use a combination. We bring down the water content not from 180 to 144 using the chemical admixture route. We bring it down to about 160. Then we try to do a little bit of trick with the mineral admixture and still move forward. The issue that we have at hand, which you must catch, there is something which I'm not telling you. I'm still insisting that a concrete which had 180 kgs of water and 400 kgs of cement and whatever sand and coarse aggregate was there, of course coarse aggregate was 1052, whatever the sand was there in the beginning, this had certain properties, certain slump, certain air content, and so on and so forth. What I'm insisting is that with this 180 kgs of water, instead of 400 kgs of cement, even if we use 320 kgs of cement and 80 kgs or 106 kgs of mineral admixtures, we will still get the same workability. That need not happen. And therefore, this discussion that we've had in terms of working only with the mineral admixture route or only with the chemical admixture route, that's true with the chemical admixture discussion as well, that a concrete which had 180 by 400 kind of a distribution and the rest of it being sand and coarse aggregate, and the other concrete that we had was 144 by 320, this will have the same workability. Now the amount of water has gone down, you have a lot more sand in the system. Will this mortar have the same properties as this mortar? Now that remains a slightly open question. Of course, there is some chemical admixture sitting here as well, which will help you, but that is why we need to do trial mixes. We need to do trial batches to make the finer adjustments. So what we've done here is only a first run, and the rest of it of course has to be done through laboratory trials. Now if we compare the options, this is what we started with, and that's what I was trying to explain to you in the previous slide. 180, 400, 629, 1052 goes to 144, 320, 790, 1052 using only the chemical admixture route. And then if we use the mineral admixture route, this is the proportion that we have. Please note that this diagram is not to scale. So don't try to read this diagram from that point of view, except that I have tried to show a slightly increased content of fine aggregate here, reduced content of fine aggregate here, reduced amount of water here, and so on. Now, in all these cases, we have kept the coarse aggregate content to be 40% and the total water content has been kept to be 600 liters. That's something which I have explained to you, and of course it is reiterated once again. And of course the paste content is something which you need to bother about. That's the other element. The difference is in the paste content compared to 1, because in 1 the paste content is this plus this. This is much lower. I'm leaving it to you to work out the volumes. I'm not showing you the volume or the volumetric comparisons, but when it comes to volumetric comparisons, you will realize that the paste in the second concrete is much less compared to the first concrete, and that is something which has to be studied further before we can finalize this mix. As far as the paste content is concerned, the obvious question or the second question that you will have or you should have is, how will the mineral admixtures be counted? Will they be counted towards the paste or not? My answer to that is yes. The mineral admixtures should be counted towards the paste, not because the mineral admixtures behave like cement as far as hydration is concerned. That is not the question here. The issue is that mineral admixtures typically have the same fineness as cement. By and large, it's comparable, and therefore mineral admixtures plus cement plus water, this is what constitutes your paste content. And to that extent, perhaps your paste content in this mix here may be slightly more than the paste content in the original mix. Now, how it helps you or it does not help you is a different story. Changes in paste content are being compensated by the change in the fine aggregate content here in order to keep the mortar content the same, that is at 60% of the total volume, that is 600 liters. With this discussion that we've had today, I would think that you have some insight into the kind of logic or the model that I have been kind of presenting to you, that a concrete is nothing but the suspension of coarse aggregates in mortar, and mortar is nothing but a suspension of sand particles in paste, and paste is nothing but a suspension of cement in water. So that is the kind of backdrop in which or with which we close our discussion for today, and I am grateful to all my teachers and my students who have helped me understand this material so much better than I did when I started my career about 40 years ago. Thank you, and I look forward to seeing you once again with further discussion on development and applications of special concretes.